Hello everyone and welcome back to part B, exercise questions answered and explained from some basic concepts of chemistry. I am Priyanka from Achievers Hunt and today I am back with the remaining questions from your NCERT textbook. So without any further delay, let's get started. Question number 1. In a reaction A plus B2 giving AB2. Okay. So what they have asked you is find the limiting reagent in different cases. So different mixtures are taken, reaction mixtures, different quantities of A and B, and we have to find the limiting reagent. The first case, 300 atoms of A is reacting with 200 molecules of B. In the second case, 2 moles of A is reacting with 3 moles of B. In the third case, 100 atoms of A is reacting with 100 molecules of B. Fourth case, 5 moles of A reacts with 2.5 moles of B, and in the fifth case, 2.5 moles of A is reacting with 5 moles of B. So this question is pretty direct, okay? You just have to find what is limiting reagent. If you'll remember in the very first video, I explained limiting reagent. So what is a limiting reagent? Any reagent in a chemical reaction, a balanced chemical reaction, which is in lesser quantity. So the minute it is in lesser quantity, what happens is once this reactant gets over, the reaction will not proceed further. So if in the above reaction, A is in lesser quantity and A gets over, there's nothing for B2 to react with, correct? So AB2 is not formed and the reaction just stops. So the first step in identifying a limiting reagent is to see if your reaction is balanced or not. So reaction, if you see, I have one A on both reactant and product side and two B's on both reactant and product side. So my reaction is balanced. So now the question is pretty straightforward. Case number 1, 300 atoms of A and 200 molecules of B. So definitely B is in lesser quantity over here and B becomes our limiting reagent. When 2 moles of A react with 3 moles of B, A is in lesser quantity and acts as a limiting reagent. Case number 3, 100 atoms of A and 100 molecules of B. Both are in the same ratio, so you do not have any limiting reagent. Question number 4, 5 moles of A and 2.5 moles of B. From the question, B2 is definitely a limiting reagent, and in the fifth case, A is a limiting reagent. Question number 2. Dinitrogen and dihydrogen react with each other to produce ammonia according to the following chemical equation. So you have a chemical equation which is given. I said whenever chemical equation is given for any stoichiometric calculation, check if it is balanced. So in this case, the equation is balanced. We have 2 nitrogens on either side and 6 hydrogens on either reactant as well as product side. So let's see what is the question actually. Question number 1, calculate the mass of ammonia produced if you have 2 into 10 to the power 3 grams of dinitrogen reacting with 1 into 10 to the power 3 grams of dihydrogen. So what have they given? They have given you the mass of the reactants which is there, and you have to calculate what is the mass of ammonia which is formed. So it is very easy. Calculate the mole ratios, and from that you can calculate how much of ammonia is formed. Will any of the two reactants remain unreacted? So here you have to see which is a reactant in excess. So we have to just find out which is the limiting reagent. If yes, which one and what would be its mass? So if you have any reagent in excess over here, you have to calculate back how much of it is remaining. Okay, so the first step is we understand the mass. We calculate the mass which is given to us. So dinitrogen is nothing but 2 into 10 to the power 3. So we can just multiply this 2 into 1000, which is nothing but 2000 grams. Similarly, mass of hydrogen is 1 into 10 to the power 3 grams, which is nothing but 1000 grams again. So molar mass of dinitrogen, nitrogen has an atomic mass of 14. So 2 into 14, I get nothing but 28 grams per mole. Similarly, molar mass of hydrogen is 2 into 1, which is 2 grams per mole. And molar mass of ammonia is nothing but 14 plus 3 into 1, which is nothing but 17 grams per mole. Now let's quickly calculate. According to my reaction, 1 mole of dinitrogen is reacting with 3 moles of dihydrogen to give me 2 moles of ammonia. So this is what information I get. So this is the information that I'm getting from my balanced equation. Okay, so let's calculate as per this mass, how many moles of dinitrogen are there? So I just divide 2000 divided by 28, which is nothing but 71.43 moles. I have my dihydrogen, which is nothing but 1000 divided by 2, that is 500 moles. Now, what is my equation telling? 1 mole will react with 3 moles of hydrogen. So, if I have 71.43 moles of dinitrogen into 3 times, it will react 3 times with the moles of hydrogen. So, 71.43 into 3 is nothing but 214.29 moles of hydrogen is required. But how much do I have? I have 500 moles of hydrogen. So, definitely hydrogen is not just enough, it is in excess, which means dinitrogen is my limiting reagent. Okay. Question number 2 was calculate the mass of ammonia which is formed. Okay. So if I have from my question, if you see from my balanced equation, 1 mole of dinitrogen gives me 2 moles of ammonia. So 71.43 moles of dinitrogen will give me 2 into 71.43 moles of ammonia, which is nothing but I get a total of 142.86 moles of ammonia. Now from the formula, I know number of moles is given mass by molar mass. So if I calculate from here, my given mass is nothing but my number of moles, my given mass will be nothing but moles into molar mass, which is nothing but 142.86 into molar mass is 17, which gives me 2428, which gives me 2428.57 grams, which I can write in the scientific notation as 2.42857 into 10 to the power 3 grams. So my second question is answered, and my third question is, if at all any reagent is in excess, we know that hydrogen is in excess by what amount? So if I just subtract the amount of hydrogen that I have, which is 500 moles, subtracted from the moles which I use, that is 214.29 moles, I get how many moles are remaining. Now this mole, if I multiply with my molar mass, I can calculate the mass of hydrogen which is remaining. So that is what we have done. We have 214.29 moles of hydrogen which is used. So the amount which is unused is 500 minus 214.29, which is nothing but 285.71 moles. Now coming back to, if I have so many moles, I have number of moles, I know the molar mass is 2. So if I multiply my moles with molar mass, I get the mass which is being unused, so which is nothing but 571.43 grams. If you want to write it in scientific notation, you can write 5.7143 into 10 to the power 2 grams. Number 3, how are 0.50 moles of sodium carbonate and 0.50 molar sodium carbonate different? Okay, so this question is pretty direct and you may get confused. Remember, whenever I have this capital letter M, in the previous video I have told, this M represents molarity. Okay, so molarity is what? How many moles are there in per liter, volume of a solution in liter. Okay, so basically here what am I doing is I'm taking sodium carbonate and I'm putting it in some solution in water, and then I'm seeing the concentration of that entire solution which is formed. So I have solute and solvent which is mixed, and the entire solution's concentration is given in terms of molarity. Whereas moles on the other hand is nothing but a representation of amount of a substance which is there. So over here you just have 0.50 moles. It is the amount of substance. It is not dissolved in anything as such over here. So if you see, molarity is nothing but moles of a solute and volume of a solution in liters. Okay. So 0.50 moles basically means here you have only 1 liter of solution, whereas 0.50 molar can mean it is not just 1 liter, it can be different moles. So if you calculate, molarity is nothing but moles by volume in liter, correct? So 0.50 molar means I have 0.05 moles in 1 liter, correct? But on the other hand, if my molarity is 0.5 and number of moles in, suppose I take 100 ml of solution, okay, 100 ml is nothing but 100 divided by 1000, which is 0.1. So I get number of moles to be 0.5 into 0.1, which is 0.05. Okay, so you can see the calculation here. So remember, whenever I just say 0.50 mole and I don't tell you how much volume is there, it is for 1 liter and it is amount of sodium carbonate in 1 liter. Whereas when I give you the molarity, it can be in different volumes that you need to find out. It can be 100 ml, it can be 200 ml, whatever, but it's a different volume. Question number 4. If 10 volumes of dihydrogen gas reacts with 5 volumes of dioxygen gas, how many volumes of water vapor would be produced? So here, the first step you need is you need to understand the reaction. So it is given over here. Dihydrogen is what? H2. And you have dioxygen, which is nothing but O2. And what is formed over here? Water vapor. Water vapor is nothing but H2O. Okay. So step 1 is you understand the reaction. Step 2 is you see if the reaction is balanced or not. So 2 hydrogens on either side, balanced. But on the reactant side, you have 2 oxygen and only 1 oxygen on the product side. So if I put a 2 over here and a 2 in front of my dihydrogen, I get a balanced equation. So what does it mean? 2 volumes hydrogen react with 1 volume oxygen to give me 2 volumes of water vapor, correct? Now my question is, I have 10 volumes of hydrogen and 5 volumes of oxygen. So if you see the ratio over here, again the ratio is nothing but hydrogen to oxygen, dihydrogen to dioxygen is nothing but 2:1. So definitely I will end up getting 10 volumes of water vapor. It is neatly explained again, you can just go through the answer, okay? The ratio remains the same. So this is the law of combination of definite volumes. Question number 5, convert the following into basic units. Okay, so you have basic units are what? SI units that you have. In length it is meter, in case of time it is seconds, and in case of mass that you're seeing it is kilogram. So here you have 28.7 picometer, you have converted to meter, 15.15 picometer again to meter, and 25365 milligram which you have to convert to kilogram. Okay, so let us quickly see. The previous video I have explained to you the conversions, the fixes and the multiples which need to be used. So picometer, we know that 1 picometer is nothing but 10 to the power minus 12 meters. So if I have 28.7 picometer, it is nothing but cross multiply. This will be x. X is equal to 28.7 into 10 to the power minus 12 divided by 1 meter. Correct? So this is nothing but 28.7 into 10 to the power minus 12 meters. And if I have to represent it in terms of my scientific notation, what I do is I bring this decimal towards my left hand side, which is 2.87 into 10 to the power. So whenever I get my decimal to the left hand side, I've told you, you add an integer. So it will be minus 12 plus 1 is 2.87 into 10 to the power minus 11 meters. Similarly, 15.15 picometer also we can do. It is nothing but 15.15 into 10 to the power minus 12 meters. So I get my decimal towards the left hand side. I get 1.515 into 10 to the power minus 11 meters. Converting your 25365 milligrams. So I know 1 milligram is nothing but 10 to the power minus 6 kilogram. So if I have 25,365 milligrams is how many kilograms? You can just cross multiply, you get nothing but 25,365 into 10 to the power minus 6 kilograms. So if you have to represent this in terms of scientific notation, remember decimal is after 5 over here, so you take it to the left. 1, 2, 3, 4. So you need to add 4 to this scientific notation, which is 2.5365 into 10 to the power minus 6 plus 4, which is nothing but 2.5365 into 10 to the power minus 2 grams. Which one of the following will have the largest number of atoms? Okay, so slightly tricky question over here. You have 1 gram of Au, nothing but gold, 1 gram of sodium, 1 gram of lithium, and 1 gram of Cl2, that is nothing but chlorine gas. Okay, So how can you find out largest number of atoms? First see 1 gram corresponds to how many moles. Okay. Once you know the number of moles, you know 1 mole has Avogadro number of particles, which is 6.022 into 10 to the power 20. So in your given number, suppose we find for gold, it has X moles. So X moles will have how much? X into Avogadro number of atoms. So in individual case, you'll have to find the number of atoms, and then you will have to see which one has the largest number of atoms. So here what we are given is, we are given the mass which is there. You have to divide it by the molar mass and first find the number of moles. So in case of your gold, atomic mass is 197 grams per mole. So you get number of moles to be 0.00508 moles. Now 1 mole has 6.022 into 10 to the power 23 number of particles. So 0.00508 moles will have that number into Avogadro's number, which is almost 3.06 into 10 to the power 21 particles. Similarly, for sodium, if you calculate, please pause the slide and try to calculate. In case of sodium, the atomic mass is 23. In case of lithium, the atomic mass is 6.94, and in case of chlorine, it is nothing but 35.5 into 2, which is 70.9. Okay. So in each case, just calculate, and if you see, you get, in case of sodium, you have 2.62 into 10 to the power 22 particles. In case of lithium, we have 8.68 into 10 to the power 22 particles. And in case of chlorine, we have 1.70 into 10 to the power 22 particles. Now remember, try to put this coefficient that you have in the same unit so that you're not confused. Okay. So definitely, if you see all the 4 answers, in lithium, we have the largest number of atoms. Similarly, if you have to see the least number of atoms which are there, we get it in terms of sodium. Number 7. Calculate the molarity of a solution of ethanol in water in which the mole fraction of ethanol is 0.040. Assume the density of water to be 1. So what have they given you in the question? They have given you density to be 1 grams per ml. So what does it mean? In 1 liter it is 1 kg per liter. Okay. So basically what am I telling? My mass and my volume is the same. If at all I have 1 liter of solution, then my mass is 1 kg. Okay. So we have our mass. We have to calculate the molarity. So molarity, we know the formula is number of moles of solute divided by the volume of solution in liters. Correct? Now, what do I need to find here? In order to find the number of moles, I need to understand what is the concept of mole fraction. Now, when I said we are having concentration expression, different ways are there to express the concentration of a solution whenever you dissolve a solute in a solvent. So mole fraction is one such thing, and mole fraction is represented by the Greek letter chi. Looks like nx, but it is actually called as chi. Okay. What it means is, here you have a fraction of the moles. So if I'm referring to the mole fraction of my solute, then it means number of moles of my solute divided by the total number of moles. So it will be moles of solute plus moles of solvent. Okay. Similarly, if I want the mole fraction of my solvent, the formula is moles of my solvent divided by the total number of moles over here. Okay. So what have they given you in your question? This mole fraction for ethanol, that is your solute, because you're putting ethanol in water over here. So mole fraction of your solute, you can represent it as chi ethanol, is nothing but 0.040 units. Okay. One more thing you need to remember is, remember that mole fraction of your solute plus mole fraction of your solvent, it always ends up being 1. Okay. So chi of your solute plus chi of solvent is always 1. Since it's a fraction, when you add two fractions, you get a whole number, right? So similarly here, mole fractions of your solute and your solvent always end up being unit. That was the video, and make a note of these formulas in your formula book since we are coming across mole fraction for the first time. So with these formulas, let's see how we can solve this particular question. Okay. So what is given? Mole fraction of ethanol. I said chi ethanol is nothing but 0.040. Mole fraction of water. So I said mole fraction of your solute plus mole fraction of solvent is always 1. So here my solute is nothing but ethanol and my solvent is nothing but water. Okay. So I can find the mole fraction of water as 1 minus 0.040, which is nothing but 0.960. Okay. Molar mass of water is nothing but, from the atomic masses if we find, 18.015 grams per mole. Again, molar mass of ethanol has a formula of C2H5OH. So 2 into 12 plus 5 into 1 plus 16 plus 1. You end up getting 46.07 grams per mole. Density of water I discussed very first in this particular numerical. It's 1 grams per ml, which is nothing but 1000 grams. So you have, in 1 liter you have 1 kg, which is nothing but 1000 grams. So I hope what is given is very clear to you all. Okay. Now if we consider that we have 1 liter of solution, since the volume is not given, remember in your molarity, whatever sums, if the volume is not given, you consider it for 1 liter. Okay. So assuming we have 1 liter of the solution, that is 1000 grams of the solution, you write number of moles of ethanol, let it be N ethanol, and number of moles of water be N water. So mole fraction of ethanol will be what? Right, chi ethanol, it is nothing but number of moles of ethanol divided by total number of moles, that is moles of ethanol plus moles of water, which we know is 0.40. Now this entire fraction that I get, okay, let me try to simplify it by dividing both numerator and the denominator with moles of ethanol. Okay, so what will I get? I will get nothing but moles of ethanol, right, ETH divided by moles of ethanol, whole thing divided by moles of ethanol by moles of ethanol plus moles of water by moles of ethanol, correct? So if I cancel these two, I end up getting, so this entire value, what I've done, only numerator and denominator I've divided with moles of ethanol. So basically it gets cancelled, you're not changing anything. So this entire thing is equal to 0.040. Now I know this will become 1, again here it will be 1. So I end up getting this fraction, which is 1 divided by 1 plus moles of water by moles of ethanol is 0.40. So if I want to solve this, what will I do? I can easily solve it as 1 is equal to 0.040, sorry, into 1 plus moles of water by moles of ethanol, correct? So if I get 1 divided by 0.040 is equal to 1 plus N ethanol by N water by N ethanol. Now this one, if I get on the other side, I end up getting number of moles of water by number of moles of ethanol. The ratio of moles of water to ethanol is nothing but 1 minus 0.040 by 0.040, which is 0.96 by 0.040. And if I just solve this, I end up getting 24. Okay, so what have I got? Moles of water by moles of ethanol is nothing but 24. Okay, now how can I find moles of water? What does this relation tell? The ratio of both of them is 24. Or I can write as moles of water is nothing but 24 times moles of ethanol. Okay, now we know, we'll see the total mass. Total mass is how much? We have is 1000 grams. Why? Because we have considered volume is 1 liter. So if it's 1 liter, we know density is 1. So definitely mass is also 1 kg. So that is nothing but 1000 grams. Mass of ethanol is what? Number of moles of ethanol into molar mass of ethanol. So I get N ethanol into 46.07. Mass of water, similarly, I can write in terms of ethanol as 24 times, see, moles of ethanol is nothing but 24 times moles of ethanol. Moles of water is nothing but 24 times moles of ethanol. So this moles of water I can write as 24 into moles of ethanol into its molar mass, correct? So total mass will be what? Total mass of my entire solution is this plus this, if I have 1 plus 2, which is nothing but 1000 grams or 1 kg. So on solving this equation, what happens over here? I can just bring this entire term, I can add, take it to the other side. 1000 divided by this entire term gives me the number of moles of ethanol, which is nothing but 2.09 moles. Now, since I know the moles of ethanol, I know molarity is nothing but moles of ethanol divided by volume of in liters, volume of solution in liters, which is nothing but 1 liter, which you have considered 1000 ml, which is nothing but 1 liter. So this gives me nothing but 2.09 divided by 1, which is 2.09 moles. So remember, they have just confused you with two formulas over here. It's pretty easy. Please rewatch this particular question. Since we are doing it for the first time, you may find it little difficult to understand in one go. Please rewatch it and again look into our study material. Similar sums are given to you. Please try to solve them and we can discuss in our doubt clearing sessions. Question number 8. What will be the mass of one carbon 12, C12 in grams? So this was discussed, I think, in the second video that we were speaking about atomic mass and molecular mass. So I told you, we took a relative standard, which is carbon 12 isotope, and we gave it a certain number of, based on the number of, protons and electrons and neutrons on it, we gave it a mass. So we had given that 1 mole of carbon 12 is nothing but 12 grams. Okay. Now, we know in 1 mole how many particles are there. There are Avogadro number of particles, which is 6.022 into 10 to the power 23 carbon atoms has a mass of 12 grams. So, one atom of carbon, they have asked in your question, what will be its weight in grams? So, all you have to do is divide 12 by 6.022 into 10 to the power 3 and get your answer. So if you see, molar mass of carbon 12 is 12 grams per mole. Okay. Avogadro number is nothing but 6.022 into 10 to the power 23. We know that mass of 1 mole of carbon 12 is 12 grams. So 1 mole is 12 grams. So 1 mole has Avogadro number of particles. So one particular particle, that is one atom, will correspond to how much? That is nothing but 12 divided by 6.022 into 10 to the power 23, which I end up getting as 1.993 into 10 to the power minus 23 grams. Number 9. How many significant figures should be present in the answer of the following calculations? So basically what they are giving you here is they have given you a few decimal figures and they have asked you to do the arithmetic function. So in the first case it's a multiplication followed by a division, second case a multiplication, and third case it's a addition. Now what they are asking you is your answer that you report, your final answer, how many significant figures should it have? Okay. Now remember one thing, the rule is in case of multiplication and division, okay, you will look into your inputs. Okay, calculate the significant figures in your inputs and your answer will have the least significant figures from input. Okay, and in case of your addition that we had, this was also discussed in the very first video. Okay, in case of addition or subtraction that we do, in this case we keep the least number of decimal places from our input. Okay, so if you actually calculate this, what do we get is in the first case we have 0.02856. So the number of significant figures in this very first figure is 4 since our initial zeros are not considered. 298.15 we have 1, 2, 3, 4, 5 significant figures. In the next digit we have 112 which is 3 significant figures, and after that we have 5785 which is 4 significant figures. So once we do the arithmetic requirement, whatever is asked, that is multiply these 3 and divide it by the fourth one, our answer should have the least number of significant figures, which is 3. So on solving this particular numerical, we get 16.4857107. Okay. Now remember, our answer should be expressed in three significant figures, that is 16.4. Now this 4 we can round it up, because since after 4 we have 8 which is greater than 5, and write it as 16.5. Okay. Similarly, in the second case, 5 has one significant figure, 5.364 has four significant figures. So answer will end up having only one significant figure. And in the third case, okay, 0.0125 plus 0.7864 plus 0.2515. In the first case, we have how many decimal places are there? 1, 2, 3, 4. Second case also we have 4 decimal places. Third case also we have 4 decimal places. So answer is expressed in 4 decimal places or 4 significant figures after the decimal. Question number 10. Use the data given in the following table to calculate the molar mass of naturally occurring argon isotope. So remember, whenever you are given the isotope and you are given its abundance, all you have to do is multiply the isotope into its abundance. Again, here argon 38, 37.96 grams per moles into 0.063, and argon 40 is 39.96 into its abundance, which is 99.6. Okay, you just have to multiply it into its abundance and then add. So if I make this as A, this is B, and this is C, I just write A plus B plus C. This is my final molar mass of the naturally occurring argon isotope. When you're doing relative mass, that is when you divide it by 100. Remember that, don't get confused, because in the previous slide, once we calculated relative mass, here we are calculating the molar mass. So when you calculate molar mass, you just do isotope into abundance for A plus isotope into abundance for B plus isotope into abundance for C. So you can see the sum, we have worked it out for you. 35.96755 into 0.00337 is nothing but 0.1212. Okay. Again, 37.96272 into 0.00063 plus 39.9624 into 0.99600. So we end up getting 39.9478, which molar mass of naturally occurring argon is nothing but 39.95 grams per mole. Remember, it is rounded up over here up to 4 significant figures, considering that while adding, our number has 4 digits after the decimal. Calculate the number of atoms in each of the following. So a very straightforward question. If you have 52 moles of argon, you know 1 mole has how many atoms? 6.022 into 10 to the power 23 atoms. So 52 moles will have how much? 52 unified mass of helium. So from 52 unified mass over here, we will have to calculate how much of helium is there and then calculate the number of atoms. 52 grams, again grams, what they have given you a mass divided by the molar mass of helium and then find the number of moles. Those moles, if you multiply with Avogadro's number, you get the number of atoms. So as I said, first one is very straightforward. If you have 52 moles, 52 into 6.022 into 10 to the power 23 is nothing but 3.131 into 10 to the power 25 atoms. 52 unified mass of helium. Okay, now we know one unified mass of helium, one atom of helium is nothing but 4 unified. This is basically the atomic mass. Okay, atomic mass of helium, which is 4 unified mass. Okay, so 52 unified mass basically means how many atoms are there. So it is nothing but 52 by 4, which is 13 atoms. 52 grams of helium. So molar mass we know is 4 grams per moles. Number of moles we have is 52 by 4, which is given mass by molar mass. So we have 13 moles. 13 moles corresponds to how many atoms into 6.022, which is 7.829 into 10 to the power 24 atoms. Question number 12. A welding fuel gas contains carbon and hydrogen only. Burning a small sample of it in oxygen gives 3.38 grams of carbon dioxide, 0.690 grams of water, and no other product. A volume of 10 liters measured at STP of this welding gas weighs 11.6 grams. So from this data, we need to calculate the empirical formula. molar mass of the gas and molecular formula. So what we have to do here is, we know that carbon on combustion with oxygen gives us carbon dioxide. The amount of carbon dioxide which is produced is 3.38 grams. So we need to calculate how much of carbon has been used. In the same way, we know that hydrogen on reacting with oxygen gives us water or water vapor which is formed. So we need to see from that water vapor how much of hydrogen has been consumed from the gas. From there, we back calculate our moles, get it to the smallest ratio, and calculate a empirical formula. So we know that mass of carbon dioxide produces 3.38 grams. We also know that 12 grams of carbon, which is the molar mass of carbon, will react to give 44 grams of carbon dioxide. So if 3.38 grams of carbon dioxide is formed, how much of carbon has reacted we have to find out, which is nothing but 3.38 into 12 by 44. So this gives us the mass of carbon which has been used, which is 0.922 grams. From knowing the mass of carbon, we can calculate the moles of carbon which have been used by dividing it with its molar mass, which is nothing but 0.0768 moles. Similarly, for water, if we see, we know that 0.690 grams of water is formed, which means if I have 18 grams of water which is formed, 2 grams of hydrogen has reacted. So similarly, if I have 0.690 grams of water which is formed, how much of hydrogen has reacted? Same way, if I calculate, I get 0.0767 grams. And from that, if I divide it by the molar mass of hydrogen, I end up getting 0.767 moles. Now, whenever we find our empirical formula, I have told you, from the moles that we get, we have to change the moles to the simplest ratio by dividing it with the smallest number. Divide both of them and we get a ratio of 1:1. So this tells us that carbon and hydrogen are in the ratio 1:1, which is nothing but CH. This is my empirical formula. So once I know empirical formula, I have to calculate the molar mass. How do we calculate molar mass? We use the ideal gas equation which is there. So to calculate the molar mass, we use the ideal gas equation. We know that molar volume at STP is 22.4 liters per mole. So what we have to see here is moles of a gas at STP is nothing but given volume which is there at STP divided by molar volume at STP, which is 10 by 22.4. So we get 0.4464 moles. Now this is the moles. From moles, how do we calculate the molar mass? We divide the given mass divided by the number of moles, which gives us a molar mass, that is nothing but 26 grams per mole. Now since we know our molar mass is 26 grams per mole, let's calculate how much is our empirical mass. We know empirical formula is CH, mass of carbon is 12, mass of hydrogen is 1, so our empirical mass will be 13. But our molar mass is nothing but 26 grams per mole. So how can we convert this 13 to 26? If we actually see, 26 divided by 13 is nothing but 2. So this is the value we need to multiply with our empirical mass in order to get a formula. So if we do CH into 2, we get C2H2, which is nothing but ethene gas. Question number 13. Calcium carbonate reacts with aqueous HCl to give calcium chloride and carbon dioxide. And as per this reaction, calcium carbonate reacts with 2 moles. 1 mole of calcium carbonate is reacting with 2 moles of HCl to give you 1 mole of calcium chloride and 1 mole of carbon dioxide and 1 mole of water. So the reaction is given to you. You have to calculate what mass of calcium carbonate is required to react with 25 ml of 0.75 molar HCl. So the question is slightly indirect over here. What you have to do is, you are given the molarity of HCl. So we know that molarity is nothing but number of moles divided by the volume in liters. Okay, so number of moles is not given to us, instead molarity is given. So if you multiply the molarity, which is 0.75, into the volume in liters, so if you have 25 ml, it is 25 divided by 1000, which is nothing but 0.025 liters. We get the number of moles of HCl. Okay, now consider that moles is X. Okay, if I know that 1 mole of calcium carbonate reacts with 2 moles of HCl, I need to see how much calcium carbonate will react with X moles of HCl. So then I find out what is the moles of calcium carbonate which is reacting, and from that I can back calculate the mass of calcium carbonate which is reacting with HCl. Of HCl is nothing but molarity into volume as discussed, which is 0.75 given in the question, into 0.025 since we have converted 25 ml into liters, which gives me 0.01875 moles. So we know the mole ratio that 1 mole of calcium carbonate will react with 2 moles of HCl from a equation which is given to us. Therefore, the moles of calcium carbonate which are formed is 0.01875 divided by 2. So you can see here, we know 1 mole of, if this is calcium carbonate and this is HCl, needs 2 moles of HCl. So if we have 0.01875 moles, how many moles of calcium carbonate are formed? So it is nothing but 0.01875 divided by 2, which is 0.009375 moles. Molar mass of calcium carbonate we know is 100 grams per mole. We have already discussed this calculation in the previous slides. So if we calculate this number of moles into its molar mass, we end up getting what is the mass which is reacting with HCl. Question number 14. Chlorine is prepared in the laboratory by treating manganese dioxide, that is MnO2, with aqueous hydrochloric acid according to the following reaction. So we have a balanced reaction wherein 4 moles of HCl is reacting with 1 mole of manganese dioxide to give you 2 moles of water, 1 mole of manganese chloride and 1 mole of chlorine gas which is formed. So how many grams of HCl react with 5 grams of manganese dioxide over here? So this is similar to the previous question. So kindly pause the slide here, try to solve it by yourself and then get back to resume the video and get back. Okay. From our question, what we need to back calculate is 5 grams of manganese dioxide corresponds to what moles of manganese dioxide, and then use the ratio and find out how much of HCl is reacting. Okay. So molar mass of manganese dioxide is given. Manganese molar mass is 54.938 grams per mole. And since 2 oxygens are there, we do 2 into 16. So on adding, we get 86.938 grams per mole. Similarly, molar mass of HCl is mass of hydrogen, which is 1, plus that of chlorine, which is 35.5. So we get 36.5 grams per mole. So we see what is the moles of manganese dioxide that are formed. Okay. So if we know the molar mass and we know the mass of manganese dioxide which we have, we know that dividing the given mass by the molar mass will give us number of moles, which is nothing but 0.0575 moles. Okay. So from my balanced equation, I have 4 moles of HCl will react with 1 mole of manganese dioxide. So how many moles of HCl will react with 0.0575 moles of manganese dioxide? It's simply a cross multiplication where you do 4 into 0.0575 divided by 1. So we end up getting 0.23 moles. Now from this data of 0.23 moles, we need to calculate what mass is it corresponding to. So what do? We know moles is mass by mass. So if you know the number of moles and molar mass, we can easily find the mass, which is nothing but number of moles, that is 0.23, into the molar mass of HCl, which is 36.5. So we get 8.395 grams, which is reacting with 5 grams of manganese dioxide. So with this, we come to the end of part B from some basic concepts of chemistry exercise questions. We have 2 more upcoming videos where we will be sharing some exemplar questions so that there is much better understanding of this concept. Till then, keep learning, keep growing. Thank you.